I posted some extra homework examples with the slides for this chapter. Um, these are maybe a little bit more challenging, so I'm going to give you kind of a little bit more guidance than I did with the last chapter's problems. In this example, we have a 1 centimeter cubic box and the edges are aligned in the X, Y, Z axes, and it's sitting in an electric field given by 350 times X, that's the X coordinate, plus 130 times in the Y direction, newtons per coulomb. Our coordinate X is given in meters. What's the net electric flux through this box and what's the charge on the box? I'm not going to go through this problem number by number, but I'm going to try and give you all the information you need to solve it and give you enough of the steps so that you can follow everything along. So first I'll draw my box. It's in the X, Y, Z coordinate system. I'm putting one of the origins at the corner. There's X, there's Y, there's Z. So we know that electric flux is given by the integral of E dot dA. Here our electric field is a variable, so we're certainly going to have to do the integral. And our cube has 6 faces, so we're going to have to do this 6 times, once for each face. Okay, let's start with the right-hand face. So let's start with this face right here. So I'll write down Gauss's law. So one right face. And why don't we even just shade that in so we remember what we're talking about. So there's the right-hand face. Let's write down Gauss's law. Net electric flux is the integral of E dot dA. What are we going to put in for our E value? Well, E is equal to 350 times X plus 130. That's in the J direction, newtons per coulomb. X is equal to the X coordinate. When we're right here on this right face, every single position of X is the same. So everywhere along this face, right here, this is where X equals 0.01 meters. So X is equal to 1 centimeter right here. So our electric field vector then is equal to 350 times 0.01, which is going to give us 3.5, plus 130 J hat newtons per coulomb. So our electric field vector is 133.5 J hat newtons per coulomb. Okay, there's our electric field vector. We might notice now that this electric field is a constant. Let's go ahead and put this in our Gauss's law and see what happens. Net electric flux for our right face is the integral of 133.5 J hat newtons per coulomb dotted with dA. Well, our electric field is a constant, so we can take that outside of the integral. So 133.5 J hat newtons per coulomb dotted with the integral of dA. The integral of dA is just the area vector. So now I've got 100, now I wish I'd just left this as an E instead of writing it out. J hat newtons per coulomb dotted with the area of the right-hand face. So what's the area of the right-hand face? The area vector points straight out of the face. So it is in the X direction. So there's our area vector. And the area of the face is just going to be the length times the width. So 0.01 meters times 0.01 meters in the X direction, so I hat. Okay, let's put that in our equation. Got 133.5 J hat newtons per coulomb dotted with our area, which is going to be 1 times 10 to the minus 4 meters squared, I hat. Okay, so now I can take my numbers out front. 133.5 times 1 times 10 to the minus 4 is 0.01335 newtons times meters squared per coulomb. Then the vector business is at the end, J dot I. Here's where we have to be really familiar with our vector product. J dot I is equal to 0. Oh, I think I said vector product. I certainly meant scalar product. Here we have j dot I. J dot I is called the scalar product or the dot product. Sorry if I said something different. What we know about scalar products is j dot I is equal to 0. Okay, so something dotted with itself, a unit vector dotted with itself is 1, dotted with a different unit vector is 0. So our answer for the electric flux for the right face is 0.01335 times 0 equals 0. So the net electric flux through the right face is equal to 0. Okay, right face is done. Let's do the left face next. So our left face is over here. Let's try and move through this a little bit more quickly. What is the electric field at the left face? At the left face, x equals 0. So our electric field vector is 350 times 0 plus 130 j hat newtons per coulomb. Our net electric flux is going to follow the same method as what we did for the right-hand face. So our net electric flux is equal to the integral of E dot dA. Our E is a constant, so it's E outside of dotted with the integral of dA. So it's E dotted with the area vector. The area vector this time is going to have the same magnitude, but it's going to point in the opposite direction because it sticks out of the face, so it points towards negative I. So for our flux, we are going to have 130 j hat newtons per coulomb dotted with our area vector 0.01 times 0.01, 1 times 10 to the minus 4 meters squared in the negative I hat direction. Here again, we've got a j dotted with an I gives us 0. Okay, there's the left face done. Let's tackle the top face next. This one might take us just a little tiny bit more time to get through. So for our top face, we're still going to use the same idea. So for the top, net electric flux equals E dot dA, taking the integral of it. Okay, so for our top face, let's shade that in, make sure we know which one we're talking about for the top face. For our top face, it's different from what we had for the left or the right face. On the right face, x was equal to 1 centimeter. On the left face, x was equal to 0. On the top face, x starts at 0 and it stops at 1 centimeter. X varies. So if we write down our expression for electric field, E equals 350x plus 130 j newtons per coulomb, we have to remember that x varies, and it varies from 0 to 0.01 meters. Okay, so x is not a constant here. So that means electric field cannot come out front of our integral, and we're going to have to integrate with respect to the area. So let's remember what dA stands for. dA is an area element. It's a little bit of the area, and when we add up all of the dAs, we get the total area. So it's an element of area A. For my element of area A, I'm going to pick a rectangle that extends over the entire length of my cube, the entire top face. So that's what I'm going to call my dA. And I like this one because if I add up all of the strips along the entire face, ultimately I'm going to cover the entire thing and I will get the complete integral. So my dA is a vector. It points straight up. The direction is in the up direction. That's j hat, the same as y. The magnitude of my dA is going to be the magnitude of the area of this little strip. It's got a length that I might call L. L equals 1 centimeter. And it's got a width that's a little bit in the x direction. So I'm going to call that dx. So my dA then has a magnitude of L times dx, and it has a direction of j hat. So that's the hard part about doing this. And then I might fill in that that's 0.01 times meters times dx j hat. Okay, let's put this in our integral now, and this is going to be an integral that's not too hard to deal with. Our net electric flux is equal to the integral of the electric field, 350 times x, plus 130 j hat. I think just for convenience, I'm going to drop the units at this point, just so it doesn't get too messy, times 0.01 dx in the j hat direction. Okay, so we're going to have to split this up, or first of all, let's multiply our 0.01 in both terms. So that's the integral of 3.50x plus 1.30 j hat dotted with dx times j hat. Let's deal with our scalar product next. So this is equal to the integral of 3.5x plus 1.3. Move my dx to the left a bit. I'm left with j dot j. When we take the dot product of two unit vectors are the same, that's equal to 1. They have a magnitude 1 and they're parallel, so 1 times 1 times cosine 0 gives us 1 if we're evaluating our scalar product. So now we've got the integral of 3.50 times x times dx plus the integral of 1.30 times dx. So because we added the two terms, we can split our integral into two bits. We're integrating from x equals 0 to x equals 0.1. That's on both integrals. So the integral of 3.5 times x is equal to 3.5 times x squared divided by 2. That's going to be evaluated at 0.01 and 0. Plus the integral from, my goodness, so easy to make a mistake. The integral of 1.3 times dx is 1.3 times x, going to be evaluated at 0.01 and 0. So that's going to give us, when we put our limits in and we evaluate it, we get 0.01318, and the units are newtons per coulomb times meters squared. So that's the flux through the top face of the cube. For our bottom face of the cube, it's pretty much the same as the top face, but for our bottom face of the cube, so for this one right here, when we pick our little element of area, there's our dA. The dA vector has to point straight out of the face, so this time it points down. When it was the top face, dA pointed up. When it was the bottom face, dA points down. That's the only difference. So we're going to say for the bottom face, same as top, except dA equals minus 0.01 times dx j hat. Okay, everything else is going to be exactly the same. When you get your final answer, you should find that the net flux is negative 0.01318 newtons per coulomb times meters squared. Okay, so right and left, top and bottom are done. Our front and back faces now are almost the same as our top and bottom faces. So for our front face, this is our front face. So we've shaded it in. We see that x varies. We need to identify some little bit of area. I'm going to pick a rectangle that has a width dx and a length L. So my dA points straight out. It has a magnitude of length times width, 0.01 meters times dx, and the direction is in the plus z direction, k hat. From there, everything else is the same as the top. So we'll do and same as top. What we end up getting for our net electric flux is we end up seeing eventually we have a j dot k and we get our flux equals 0. For our back face, so that will be this back face right here. We have to shade in a little area element. Again, we'll take a little strip of it. The vector points straight out. So for our back face, dA equals 0.0100 dx times negative k hat. And I'm not sure how clear that negative is. Why don't we just rewrite it? There, I think that's more obvious. And after we put in that dA, otherwise the steps are the same as the front face. And we get that our net electric flux through the back face is equal to 0. When we add up all of our fluxes, the total electric flux is the sum of all 6. What we get is it's equal to 0. Okay, so our net electric flux through this box is equal to 0. That brings us to our final answer. What is the charge in the box? If we remember that net electric flux by Gauss's law is also given by the net charge enclosed divided by epsilon naught. If the flux is zero, the charge is also zero. We have another extra problem now that builds on a homework problem that we had in a previous lecture. We have a long insulating cylinder. It has a charge on it, and that's uniformly distributed. And around this insulator is a conducting cylindrical shell. We know the inner and outer radii, and that conductor is charged as well. So we have a cylinder surrounded by an insulating cylinder surrounded by a conductor, and both things are charged. We're asked to figure out some things about the charges in the electric field. Let's start with a picture. I've preloaded a diagram here just so that it's nice and neat and easy to look at. By all means, you can draw your own by hand. So it's just for an illustration. So our insulating cylinder is here in the middle. That's the blue one. Our insulating cylinder has a radius r, and r is equal to 5 centimeters. It's a charged cylinder, and we know the charge density. We see that the charge density is given in units of coulombs per meters cubed. That makes it a volume charge density, so it has symbol rho. So this bit is our insulator, and we know that the charge density of our insulator is 300. Oh, hang on. I was going to write 300 microcoulombs, but why don't I just write down the number that was given? 3.00 times 10 to the minus 4 coulombs per meters cubed. Cubed because it's a volume charge density. Okay, the insulator is concentric. It means it has the same centers with a conducting cylindrical shell. So this bit right here is the cylindrical shell. Picture it like a paper towel roll maybe, or a rolled up sheet of paper. So that's what this likes, and there's a solid core inside. The cylindrical shell has an inner radius. So from here to here, that's Ri, and it has an outer radius that's called Ro, and those numbers are given in the problem. Ri is 7.5 centimeters, Ro is 8 centimeters. The conductor is also charged, so this bit is the conductor, and we're given the linear charge density for the conductor. We see that that has units of coulombs per meter. So that's lambda equals minus, negative charge there on this one, minus 4.25 times 10 to the minus 6 coulombs per meter. Okay, now we've got our setup nice and clear. We'll get started on part A. For part A now, we're asked to find the inner and outer surface charge densities on the conductor. So these are surface charge densities. What we're trying to find is sigma, and that's going to be the charge, Q, divided by the area. So let's make sure we understand what's happening. Our insulator, and we have here on the left a 3D view. It's probably easier to look at a 2D view. So our insulator is full of positive charge. Let's just represent that with a few pluses. It's uniformly distributed over that whole volume. And our conductor also has some charge, but let's think about what's happening in the conductor. In a conductor, charge is free to move around. If this insulator is positively charged, then some negative charges are going to be attracted to this inner surface. So what's going to happen is that on the inner surface of the conductor, we're going to get some negative charge. Okay, those are all minus signs. The amount of charge, let's call that Q, and let's put an I on it for inner surface. Qi equals charge on inner surface of conductor. We'd like to find out how much charge is here because we need to do the charge divided by the area to figure out the charge density. So to figure out the charge, let's think about something we know. And one fact we know about conductors in static equilibrium is that the net electric field in the conductor is zero. So what I'm going to do is I'm going to draw a Gaussian surface in the conductor. So that's my red line I'm drawing right here. So there's a Gaussian surface, and it's inside the conducting shell. If I were to draw it in 3D, it would see that it also goes over the length of the shell too. Okay, so my Gaussian surface, I'm going to say GS for Gaussian surface, is cylinder, inside the conductor. And I'm picking it there because I know the electric field in a conductor is 0. So now that I've got that, I'm going to write down my Gauss's law expression. My Gauss's law says the net electric flux through any surface is equal to the electric field dotted with the area is equal to the charge enclosed by the Gaussian surface divided by epsilon naught. Now my electric field equals 0. That tells me that my Q inside must be equal to 0. So the net amount of charge inside this red dotted line has got to be 0. So my total charge has to be 0. So let's think about what that means. So Q in is the total charge inside the Gaussian surface. That's equal to, let's add up the things that have charge. The inner surface of the conductor has charge, so it's equal to the charge on the inner surface, and the insulator has a charge. So now we have to put all these things together. We know that the Q inside is equal to 0. We're trying to find the Q on the inner surface. So the last bit we need to solve this puzzle is how much charge is on the insulator. So now on this slide, I've just copied all of the previous slides, so we have all of our information together. The charge on the insulator is going to be the charge density times the volume of the insulator. The volume of the insulator is given by pi times its radius squared times its length. And let's call that length L. Okay, these are numbers that we know. So we can fill that in here. I'll just wait one more step. So now from this expression, I'm going to solve for the charge on the inner surface. Charge on the inner surface is the net amount of charge enclosed by the Gaussian surface. Take away my charge on the insulator equals 0 minus my charge on the insulator equals minus rho times pi times r squared times L. Okay, so my Q inside then, my Q on my inner surface, Qi is going to be minus rho times pi r squared L equals minus, my rho is equal to 3.00 times 10 to the minus 4 coulombs per meter cubed times pi times r squared. R was 5 centimeters, 0.05 meters squared times my length L. I don't have a length, I'm just going to leave that as L for the moment. So there's my charge on the inner surface. I'm asked to find the charge density. My charge density sigma is going to be my charge on the inner surface divided by the area of the inner surface. Okay, here's where this L is going to get taken care of. So my charge on the inner surface, if we work this out on our calculator, what we get is minus 2.356 times 10 to the minus 6 times L. My area of my inner surface is the area of that cylinder. It's 2 pi r. So we're talking about sigma equals Qi over area of the inner surface equals Qi divided by pi, 2 pi r, radius of the inner surface times the length. Okay, so 2 pi r times the radius of the inner surface, we were given that that was 7.5 centimeters. 0.0750 meters times the length L. So we see that our L's cancel and we're left with our charge density equals minus 5.00 times 10 to the minus 6 coulombs per meter squared, or minus 5 microcoulombs per meter squared. This is an area charge density because it's charge over area. So there's my charge density on the inner surface. Next we'll do the outer surface. So let's sort out how we're going to find the charge density on the outer surface. Our charge density on the outer surface is going to be our charge on the outer surface divided by the area of the outer surface. So this is charge on outer. The area of the outer surface is going to be given by 2 pi r of the outer surface times the length of the outer surface. As a reminder, our insulator was full of positive charge. That attracted an amount of negative charge to the inner surface. We called that Qi. And then the remainder of charge on the conductor will sit on the outer surface because all charge on a conductor has to sit on the surfaces. Okay, so what that means is we have some charge on the inside surface, some charge on the outside surface. The total charge overall, Q of the conductor, is however much charge is on the inside surface plus however much charge is on the outside surface. So the charge on the outside surface is the charge on the conductor. Take away the charge on the inside surface. The net charge on the conductor is something we can figure out. The total charge would be the charge density times the length. And we're given that the charge density is minus 4.25 times 10 to the minus 6 times the length. The charge on the inside surface is something we found in the previous step. That was minus 2.356 times 10 to the minus 6 times L. Okay, let's put this together to find the charge on the outer surface. So we've got the Q of the conductor, minus 4.25 times 10 to the minus 6L. Subtract the Q of the inner surface, 2.356 times 10 to the minus 6L, to give us the net charge on the outer surface of the conductor, which is equal to minus 1.894 times 10 to the minus 6 times L. Okay, there's our charge on the outer surface. To get our charge density now, we just divide that by the area. So sigma for the outer surface is QO divided by area O minus 1.894 times 10 to the minus 6L divided by 2 pi. The radius of the outside was 8 centimeters. L, we see that our L's cancel, which is good. And we're left with a charge density of minus 3.77 times 10 to the minus 6 coulombs per meter squared. Okay, there was kind of a lot of work to it, but overall we had to find the surface charge density, which was charge divided by area, and we figured out the charge first by thinking about Gauss's law and second by thinking about the net charge on the conductor. For part B, we're asked to find expressions for the electric field inside the cylinder, between the cylinder and conductor, inside the conductor, and outside the whole thing. So for this part, we know we're going to use Gauss's law. Net electric flux is the integral of E dot dA equals the charge enclosed by our Gaussian surface divided by epsilon naught. Let's deal with the integral part of Gauss's law in cylindrical symmetry first. So whenever we have a cylinder of charge, the net electric field is going to be radial. So radially out if the charge is positive, radially in if the charge is negative, but always radial. That means our choice of a Gaussian surface is going to be a cylinder with radius r and length L. So let's draw a Gaussian surface. Doesn't really matter if we put it inside or outside because we'll get the same behavior. And we've done this a few times now, so I'm going to try and skip through it fairly quickly. Our net electric flux is going to have three terms. Net electric flux through the front, plus the net electric flux through the back, the two faces of the cylinder, plus the net electric flux through the wall of the cylinder. The net electric flux through the front face of the cylinder is going to be the integral of E dot dA. Our front face is this, oops, meant to grab my laser pointer. The front face of the cylinder is right here. A little bit of area sticks radially out from the face. So the area vector and the electric field vector are perpendicular. Oops, wrong color. So that's equal to the integral of E times dA times cosine 90 degrees gives us 0. The electric flux through the back face is going to be the same thing. The little bit of area going through the back face sticks perpendicular to the electric field. So there's our dA for the back face. That's perpendicular. So the net electric flux is the integral of E dot dA equals the integral of E times dA times cosine 90 equals 0. Okay, we're left with the net electric flux through the wall of the cylinder. A little bit of dA on the wall of the cylinder is going to be radially outwards. Our electric field is radially outwards, so those two vectors are parallel. The net electric flux through the wall is the integral of E dot dA equals the integral of E times dA times cosine 0. That's equal to 1. The integral of E times dA. If we're the same distance, so if we're on the surface of this cylinder, it means our electric field is a constant. E outside the integral of dA. The integral of dA is just A, which is the area of a cylinder, which is 2 pi r times the length. And let's put the length on our diagram as well. So the net electric flux through a Gaussian surface, which is a cylinder, let's just write that down. Our net electric flux is going to be E times 2 pi r times the length. So that gives us this side of Gauss's law. The next bit we have to do is for each of the 4 spots, let's find the Q enclosed, put it in Gauss's law, and solve for the electric field. So let's start with inside the insulating cylinder. Remember, R is the radius of our insulating cylinder. So now for this part, we draw a Gaussian surface, which is going to be a cylinder of length L inside our insulating cylinder. Okay, so this has radius R, it has length L. If we want to find the charge enclosed, which is what we have to do to keep going with our equation, so we have to know Q inside. To find Q inside for R less than the radius of the cylinder, Q in is going to be the density times the volume, and we know the density, so it's density times volume. The volume of our Gaussian cylinder is pi times r squared times the length of the cylinder. So now let's put our terms together. This is Q inside, this is our net electric flux. So our net electric flux is E times 2 pi times r times the L. That's equal to our Q inside, rho times pi r squared L. And then we divide that by epsilon naught. We've got pi on either side, they divide through, L divides through, got an r on the left and r squared on the right. So this simplifies to our electric field inside the cylinder is equal to rho times r divided by 2 epsilon naught, and our direction is going to be radially outwards because that charge is positive. If you wish, you could fill in some numbers here. You could fill in your rho and your epsilon naught. I think I'll stick with symbols just because it's a little neater to look at. Okay, that's the electric field inside the cylinder. Next, we want to find the electric field between the cylinder and the conductor. So let's draw a Gaussian surface. You could draw this in 2 dimensions if you prefer. I think I'm going to try and stick with the 3D. So we'll draw a Gaussian surface, which is a cylinder. It has radius r and length L. Our Q inside is going to be the net charge on the insulating cylinder, which is inside. So Q in is equal to density times V. V is the volume of the insulator inside the Gaussian surface. Okay, so that's rho times pi times the radius of the insulator squared times the length. Put this in our Gauss's law, the net electric flux is E times 2 pi r times L. It's equal to Q inside the Gaussian surface divided by epsilon naught. Get a little cancellation going on here. Looks like only our pi's cancel this time. We solve for E. Oh wait, our L's canceled as well. Miss those. Our electric field then, we divide both sides by 2r, gives us rho times r squared divided by 2 epsilon naught times 1 over r. Because our charge inside is positive, the electric field is radially outwards at this point. Okay, next. Next one is the easiest. So we want to find the electric field inside the conductor. So Ri is the inner radius of the conductor. Ro is the outer radius of the conductor. If we were to draw our Gaussian surface as a cylinder between the inner and outer surface, we would see that it is exactly inside the conductor. So for Ri less than R less than Ro, we know the electric field equals 0 because it's in a conductor, in static equilibrium. Okay, that bit's done. Our last bit now is to find the electric field outside everything. So let's draw a Gaussian surface. And let's pick our Gaussian surface to be a cylinder that's outside everything, outside the conductor and outside the insulator. Gaussian surface has a radius of r and it has a length of L. We'd like to know the net charge inside. The net charge inside is however much charge is on the conductor plus however much charge is on the insulator. The amount of charge on the conductor is the charge density times the length. The amount of charge on the insulator is the charge density times the volume. Okay, so that's lambda times L plus rho. The volume of our insulating cylinder is going to be pi times the radius of the cylinder squared times L. Let's put this in our Gauss's law expression. The net electric flux is E times 2 pi r times the length equals our net charge enclosed, which is lambda times L plus rho times pi times r squared times L divided by epsilon naught. We only get a little bit of cancellation here. If we divide both sides by L, we have that in every term, so they cancel. Then we'll divide both sides by 2 pi r. We see that our electric field is lambda plus rho times pi times r squared divided by 2 times pi times epsilon naught outside of 1 over r. So there's our electric field. The direction of our electric field, overall the net charge is negative, so the direction of the electric field is going to be inward because the net charge is negative. For part C, you're asked to find the electric field at different spots. This is a straight up plug and chug. So for our first one, and I'm not going to work through all these numbers for you, for the first one that's inside the cylinder, the electric field is 5.08 times 10 to the 5 newtons per coulomb, and it points outward. The second one is in between the conductor and the insulator. There we've got an electric field of 7.06 times 10 to the 5 newtons per coulomb, radially outward. Third one's pretty easy. That's inside the conductor. That's where your electric field equals 0. And the fourth one is outside everything. And that's where your electric field is equal to minus 3.41 times 10 to the 5 newtons per coulomb. Because it's negative, it points radially inward. For the last bit, we're asked to draw the electric field. So let's put on our axes. We'll put our distance on the horizontal. We'll put our electric field on the vertical. The spots of interest are the radius of the insulator, the inner radius of the conductor, and the outer radius of the conductor. Okay, first bit, if we're inside the insulator, here's where the equation for the electric field was E equals rho over 2 epsilon naught times r. We see that E is proportional to r, so it's linear. Oops, proportional to little r, not big R, proportional to r. At its peak value right here, at r equals r, the electric field is equal to rho times the radius of the insulator divided by 2 epsilon naught. Okay, in between the insulator and the conductor, that's our next bit. So between insulator and conductor, our equation for our electric field in this piece right here is electric field equals rho times r squared over 2 epsilon naught times 1 over r. This tells us that our electric field falls off as 1 over r. And it'll fall off to some finite value. So it's falling as 1 over r, proportional to 1 over r in this region. Where r equals ri, this point right here, r equals ri, the value of the electric field at this place, E is equal to rho times the radius of the insulator squared divided by 2 times epsilon naught times 1 over ri, the inner radius of the conductor. Okay, so that's that next section. Ri to Ro, that's inside the conductor. The electric field in the conductor is 0. And then once we get outside the conductor, our electric field now jumps. And we know the expression for the electric field outside the conductor So for this part out here, E was equal to, oh, why don't I stick to red here for that? E equals lambda plus rho times pi r squared over 2 pi epsilon naught times 1 over r. Overall, this is a negative charge, so it's going to start at a negative value and tend towards 0 as r gets big. So this bit right here, as r goes to infinity, the electric field goes to 0. At this place here, where r equals rho, the electric field is equal to lambda plus rho pi r squared over 2 pi epsilon naught times rho. Okay, so there's a pretty complete graph of the electric field. This is kind of an interesting, which is a lot like a problem we've done before, but it challenges us to think of it in a new way. So we have an insulating sphere, that's this one right here. We know the radius and we know it has uniform charge density. We want to find the electric field inside the sphere. In a previous problem, in previous work, what we've done is we've found the electric field relative to the center of the sphere. I'm going to label that as r primed. So we've done that problem already. We know how to do that one. But this problem is asking us to find the electric field at this point, but instead of giving our answer relative to the center, give it relative to the origin of a coordinate system that's outside. So now this is our r. So we want the electric field at this point, but instead of writing it relative to the center, we want it relative to here. So let's put a couple of things together that we know. We know how to sort out what the electric field is relative to the center. And then if we look at this vector diagram, we see that vector b, so that's from the origin of the coordinate system to the center of the sphere, vector b plus vector r primed from the center of the sphere to the point we care about is equal to vector r. So let's try and put all those things together. Let's start with, can we find the electric field as a function of distance from the center of the sphere? So can we do that? So r primed equals the radial distance relative to center of sphere. To do that, we're going to use our Gauss's law. Well, why don't we write down our other condition too? Okay, so then to get E as a function of R, we'll remember that we can see that B plus R primed equals vector R. Okay, we're going to put all that stuff together. So let's find the electric field first. We're going to zip through this pretty quickly because we've already done it before. So we have our sphere of charge. We'll draw a Gaussian surface inside. The radius of our Gaussian surface is r primed. We'll write down Gauss's law. Net electric flux is the integral of E dot dA equals Q inside the Gaussian surface divided by epsilon naught. For this part, we've done this a whole bunch of times. I'm just going to say show steps. Okay, show steps to see that this part is equal to E times 4 pi r primed squared. If you don't quite remember, you can go back to where we did this example in class. Okay, next we need Q inside. Q inside is going to be the density times the volume of our Gaussian surface equals density times 4/3 times pi times r primed cubed, 4/3 pi r cubed for volume. When we put it all together, we see E times 4 pi times r primed squared is equal to rho times 4/3 pi r primed cubed, and that has to be divided by epsilon naught. That gives us a magnitude of our electric field, so we'll divide both sides by 4 pi r primed squared. It leaves us with rho times r primed divided by 3 times epsilon naught. There's the magnitude of our field. Of course, our electric field is a vector. So as a vector expression, our electric field has magnitude, rho times r primed over 3 epsilon naught, like we found on the previous slide. The direction of the electric field is radially outwards. It's in the same direction as the r primed vector. So we could write that direction as r primed hat. So here's where the unit vector notation comes in pretty handy. If we look at this, r primed times r primed hat, That's our vector, r primed. So let's write that one down. So our electric field is equal to rho times r primed, the vector, divided by 3 times epsilon naught. That gives us the electric field inside this sphere. So next we'll use our transformation, which is that since B, so that's the position of the center of the sphere relative to the origin, plus r primed, so which is the center of the point we're talking about where we're trying to find the field relative to the center of the sphere. Add those two guys up, and what we get is the vector r. The vector r is where we want to find the field relative to the origin of the coordinate system. That means that r primed is equal to r minus b. Okay, let's put that in our expression for electric field. E is equal to rho times r minus b divided by 3 times epsilon naught. And that's the expression we were asked to find. So now let's take that bit we just did and let's turn it into a new problem. Let's say we have an insulating sphere with radius r, so a great big sphere, and it has a hole that's off center. So this is kind of an interesting idea. Find the electric field inside the hole. So we want the electric field in here. So the first way we're going to think about this is how could we make this structure? So the way to make this structure, the way to make a sphere with a hole in it is we could take a solid sphere, so a solid sphere, and we could drill a hole out of it. So we could drill out a small sphere. What that would look like in terms of a picture is to get this structure, so there's our hole, the little shaded in bit, we would have to take this solid sphere and we would have to subtract, we would have to drill out this little bit. So if we took that away, then that gives us, maybe I shouldn't shade that in because that's a solid bit that we're going to take out. So if we take this solid sphere right here, and if we remove this piece, then that leaves us with this structure right here. So what that means is that the electric field of this structure is going to be the electric field of the solid sphere. Take away the electric field of the small sphere. Okay, hopefully that makes sense as a strategy. So to get the electric field of this spot right here, we'll find the electric field right here and we'll subtract the electric field of this one. So let's just recap that once more with slightly nicer pictures. So here's our sphere with the hole drilled out of it. We'd like to find the electric field somewhere here inside the cavity. So this structure, the electric field of this structure, is equal to the electric field of the solid sphere right here at the same place. And then what we want to do is subtract the electric field of this little one that we've drilled out at the same place. Okay, so hopefully this is making sense as a strategy. So E of the solid sphere, take away the E of the small sphere, gives us the electric field right inside this cavity because this is where we've drilled that hole out. So we take this field, subtract this field, it leaves us with this field. Okay, so let's start right here. We know how to find the electric field of a solid sphere, and let's do that on the next slide. So for our solid sphere, that'll be our starting point. We'll write Gauss's law. The integral of E dot dA is equal to Q inside our Gaussian surface divided by epsilon naught. Our Gaussian surface will be a sphere with radius r. The integral of E dot dA equals, we'll show all the steps like we did in the lectures, and we'll find that that's equal to E times 4 pi r squared. If this were a test question, you would certainly have to write out all these steps and show all that detail. For our Q inside, that's the net charge enclosed by the Gaussian surface, so that's going to be the density times the volume of the Gaussian surface. That's equal to the density times 4 divided by 3 times pi times r cubed. We put this together, E times 4 pi r squared equals the charge divided by epsilon naught. 4's cancel, pi's cancel. We're left with our electric field is equal to rho times r over 3 times epsilon naught. That's kind of a familiar result, so we went through it a little bit more quickly. The direction of the electric field is radially outwards. It's in the same direction as r. So to make our E a vector, we have to put it in the r hat direction. And then we recognize that this is the vector r. Okay, so let's write down that result. So our electric field of our solid sphere as a function of position relative to the origin r is equal to the charge density times that vector relative to the origin divided by 3 times epsilon naught. There's our electric field vector for the solid sphere. Our electric field of our small sphere, we can recognize that we already solved this problem in the previous question we did. So vector B gave us the distance to the center relative to the origin, and vector r was from the origin to where we wanted to find the electric field. This is exactly what we did in this problem back here. So we've got exactly the same result. The electric field of the small sphere is density times r subtract b divided by 3 times epsilon naught. Okay, now we just have to put it together. So now to finish, we know that our electric field of our sphere with the hole taken out is equal to the electric field of the solid sphere. Subtract the electric field due to the little hole that we drilled out. So let's fill in those values. Rho times r divided by 3 times epsilon naught. Subtract rho, maybe I don't need that bracket there at all. Rho times r minus b divided by 3 times epsilon naught. So that's equal to rho over 3 times epsilon naught outside of r minus b. So the result is the electric field of that structure is equal to rho times b divided by 3 times epsilon naught. And remember, b is our vector that takes us from the origin of our coordinate system to the center of the little hole. That's what B stands for. What's super interesting about this result is that the electric field in this cavity is actually a constant. It depends on rho, charge density, that's constant, B, the position vector to the center, divided by 3 epsilon naught. So that's kind of a neat result. So our electric field inside that cavity is a constant.